Hello students, today our topic is special functions. So until now we know about different functions such as algebraic functions, trigonometric, exponential, logarithmic functions. So these functions are called elementary functions. On the other hand, Bessel and Legendre functions are the special functions of mathematics. So here in this topic we are going to solve the second order differential equations by power series solution method. Before that, we are going to discuss the basic definitions such as for example, before that, consider a second order differential equation. Let's consider the differential equation, which is P naught of x d square y upon dx square plus P1 of x dy upon dx plus P2 of x into y. This is equation number 1. Here this is a second order differential equations, and here P0 of x, P1 of x and P2 of x, they are called polynomials. Here P0 of x, P1 of x and P2 of x, these are polynomials. Polynomials in x. Clear? So this is a differential equation, and now in this lecture we are going to study how to solve such a differential equation by power series method. Before that, we are going to discuss some important definitions, such as we should know that some important definitions. Clear? The first thing is ordinary point. A point at x equals to a is called ordinary point of the above equation of differential equation, which is given in one differential equation 1. If P0 of x does not equal to 0 at this point x equals to a. This means that is I can write it as P naught at point A does not vanish, then such a point is called ordinary point of the differential equation. So on the other hand, we have singular point. Singular point. Remember students, if at a point x equals to a, if this equation, this p naught of x, this polynomial at this point x equals to a does not vanish, then that point is called the ordinary point of this equation. Clear? On the other hand, if a point at x equals to a is called singular point of the differential equation 1 if p naught of x is equal to 0. It vanishes, p naught of x vanishes at this point at x equals to a, then such a point is called singular point. Clear? That means that is, I can write it as, if p naught at point a it vanishes, then that point is known as singular point. So now we are going to define the working rule for solving differential equation. Clear? Working rule for solving equation number 1, differential equation 1. So first I will write these points and then we will have an example. So in the first step, when x equals to 0 is ordinary point, of differential equation 1. First we consider that x equals to a is an ordinary point of the above equation. Later on we will discuss it for the singular point. Clear? But before we are solving the differential equation for an ordinary point. So if x equals to 0 is an ordinary point of the differential equation. So in the first step, write the given equation, write the differential equation, which is p naught of x d square y upon d x square plus p1 of x dy upon dx plus p2 of x into y. This is equal to 0. Let this is equation number first. Clear? First of all, we should write the given differential equations. Here we are given this differential equation. So we have write it. Now in the second step, now p naught of x is not equal to 0 at x equals to 0. We see here in this definition, in the ordinary point definition, we told that if at any point this polynomial p naught of x it doesn't vanish, then that point is called the ordinary point. And here we assume that x equal to 0 at this point. At this point, the p naught of x doesn't vanish, so it is an ordinary point. Clear? So this means that at x equals to 0, p naught of x doesn't vanish. That is x equal to 0. That means that x equal to 0, this point is ordinary point. ordinary point of the given differential equation. Now in the second step, consider the solution of the given equation, differential equation, in the series form as consider the series solution of differential equation 1 as in this form: y equals to a naught plus a1x plus a2x square plus a3x cube and so on up to an x to the power n and so on. Let this is equation number 2. Clear? Then using this equation find d square y upon dx square and dy upon dx. Differentiate this solution twice with respect to x and then put their values in the equation number 1. In the third step, put y for this value, dy upon dx and d square y upon dx square into equation 1 and simplify it. Clear? So after the simplification, equating after simplification, equate the coefficient of coefficients of x to the power 0, x to the power 1, x to the power 2, x to the power 3 and up to so on, x to the power n and so on to 0. Clear? So by that we will get, and it will give us the values of a naught, a2, a3, a4 and so on in terms of a naught and a1. Remember, whenever we put y, its first derivative and second derivative in equation number 1, and after making simplifications we will obtain these coefficients a naught, a2, a3, a4, and all these coefficients will be given in terms of a naught and a1. Clear? Now once we obtain those coefficients a naught, a1, a2, a3 and so on, then in the fourth step put A2, A3, A4 and up to AN and so on into equation number 2 here in this equation. A0, A1, A2, A0 and A1 are already exist, and A2, A3, A4 and so on. These coefficients will be given in terms of A0 and A1. So after putting these coefficients A2, A3, A4 and so on in equation number 2, so we will get the solution of the given differential equation. So that will be our solution. Clear? So now let's, I hope you have understand all the procedure. Let me repeat it again. In the first step, note the given differential equation, and we assume that x equals to 0 is ordinary point. That means that p0 of x doesn't vanish at that point. Then assume the solution of that differential equation in this form, which is the power series solution, and differentiate it twice. Then substitute those values, the solution, its first derivative and second derivative in the equation number 1. And after simplification, we will equate all the coefficients of x to the power 0, x to the power 1, x square, x cube and so on. So we will equate their coefficients to 0, and after that we will get the A2, A3, A4 and so on. And when we substitute those coefficients in equation number 2, that will give us the solution of equation number 1. Clear? So as an example, which is in the exercise, example, solve the differential equation, which is d square y upon dx square plus xy, which is equal to 0, by series method. So solution according to the rules. In the first step, we should write the given differential equation. Here the differential equation is d square y upon dx square plus xy, which is equal to 0. Let this is equation number 1. Here p0 of x, which is equal to 1. Here you see that here the coefficient are the polynomial, here is 1. So p0 of x here is 1. So this implies that when we put x equals to 0 here, so it doesn't vanish. So p0 of x doesn't vanish at x equal to 0. So this means that x equal to 0 is ordinary point. Of differential equation 1. Now consider the series solution of equation 1 is y equals to a naught plus a1x plus a2x square plus a3x cube and so on up to an x to the power n and so on. This is equation number 2. Now dy upon dx, or I can write it as y prime. Clear? So this will be equal to, here it will be considered constant, so it will be 0, and here the derivative of this term will be equal to a1 plus this will be 2 times a2x plus 3 times a3x square and so on, and here it will be n times an x to the power n minus 1 and so on. This is equation number 3. So again differentiating, this means that the second order derivative, which is d square y upon dx square. So differentiate this equation again, so it will be 0 again because it is constant. So we will get 2a2 plus this will be 6 a3x plus it goes on, and it will be n times n minus 1 into an x to the power n minus 2 and goes on. This is equation number 4. Now put here in equation number 1 the value of x and d square y upon dx square. Put equation number 2 and 4 in equation number 1. We get, so equation 1 will be like this one, which is, this is from equation number 1, 2a2 plus 6 a3x plus so on plus n times n minus 1 into an x to the power n minus 2 and so on, plus x times y, which is x into y. So multiply x with each of its terms, so it will be a naught x plus a1 x square plus a2 x cube and plus a3 x to the power 4 and so on, plus n times an, which is, this is an x to the power n plus 1 plus so on. So this is equal to 0. Clear? Now in the third step, as here when we were discussing in the working rule, when we put y dy d square y upon dx square in equation number 1 and simplifying it, so after simplification we will equate the coefficients of x to the power 0, x to the power 1 and so on up to equating with 0. So they will give us a2, a3 and so on. So therefore equating the coefficient of equating the coefficient of x to the power 0 to 0. Clear? So here with this term we have x to the power 0 and all the remaining terms are including x and higher power of x. So we have only this term which is 2a2. This term has the variable x to the power 0. So that means that 2a2 is equal to 0. This means that a2 will be equal to 0. Clear? Now for higher power of x, which is now equating coefficient of x with 0 to 0, sorry, to 0. So here we have x in this series, the other terms are higher power of terms and this one is a0. Clear? So therefore 6a3 plus a0, this is equal to 0. Because here we have 6a3 and here we have a0, and by equating it to 0, so a3 will be equal to, this implies that 6a3 will be equal to minus a0, or a3 is equal to minus a0 divided by 6. So this is a3. So this process will goes on, and in the next step we will equate the coefficient of x square with to 0. That will give us a4, and we will continue. So if we reach x to the power n, equating coefficient of x to the power n to 0. So now look for the terms which are the terms of x to the power n. So here this is x to the power n minus 2, and after that we will get x to the power n minus 1, and after that we will get x to the power n, And similarly here in this series we have here x to the power n plus 1, and before that we will have x to the power n. So this is x to the power n minus 2. In the next step we will have x to the power n minus 1, and after that we will have x to the power n. So by that, in that term we will have n plus 2 times n plus 2 minus 1 into a n plus 2. Clear? So this is the term. Here we have the coefficient n into n minus 1 a n, x to the power n minus 2. After that we will get n into n minus 1 into n minus 2. Clear? Into a n x to the power n minus 1, and after that we will have n plus 2 into n plus 2 minus 1 into a n plus 2. And here in the next series this is x to the power n plus 1, and before that we will get x to the power n. Before this term the coefficient will be a n minus 1 and the variable will be x to the power n. Clear? Plus a n minus 1, this is equal to 0. So a n, by this equation a n plus 2 will be equal to, it will be equal to minus a n minus 1 divided by n plus 2 times n plus 1. So this is the recurrence formula by which we can get all the coefficients. Here n will start from 1, 2, 3 and so on, because the first, if you put n is equal to 1, so we will get a3. Clear? By putting a3, we have already found a3, but let's use it as a for the checking of the validity of this recurrence formula. When n is equal to 1, so it will be a3, which is equal to a1 minus 1, so it will be a0 divided by, so 3 into 2, 6, minus a0 divided by 6. So this is the recurrence formula. So this is the formula by which we can find all the coefficients. So for, let's suppose we have found a0, a3, and now we are going to find a4. So for a4, when n is equal to 2, that will be a4 is equal to minus this will be 2 minus 1, a1 divided by 2 plus 2, 4, 4 times 3, 12. So this is now a4, and for n is equal to 3 we will get a5, as this will be 3 minus 1 minus 3 minus 1, that will be a2 divided by 3 plus 2 5, 5 plus 4, so it will be 20. Clear? But already a2 is 0, so if we substitute a2 here, this will give us a5 will be equal to 0 divided by 20, so this will be 0, so a5 is 0. And similarly for a6, when n is equal to 4 we will get a6 which is equal to minus a3 divided by 30, and a3 is minus a0 divided by 6, so this will be minus a0, so this negative sign and this negative sign will become positive, plus a0 divided by 6 3s are 18, 180, so this is a6, and we can find the remaining coefficients. Clear? So now substitute all these coefficients, that is a0, a2, a3, a4, a5, a6 and so on in equation number 2. So we will get our final solution. Now put a2, a3, a4 and so on into series solution of equation 1, which is equation number 2. So equation 2 is this one, so y will be equal to a0 plus a1x plus a2. a2 is 0, so 0 times x square plus a3 x cube, so a3 is minus a0 divided by 6 into x cube, and similarly a4 is minus a1, so this is minus a1 by 12 x to the power 4 plus a5 is 0 x to the power 5 plus a6, which is a0 divided by 180 x to the power 6 and so on. So this is the final equation, it is the series solution of the given differential equation. I can write it as a0 plus a1x minus a0 divided by 6 x cube minus a1 upon 12 x to the power 4 plus a0 divided by 180 x to the power 6 and so on. Or we can also write it as y is equal to a0 into 1 minus x cube upon 6, and here we will get plus 1 over 80, which is x to the power 6 upon 180 and so on. And for a1, this will be a1 times x minus x to the power 4 divided by 12, and so on. So it is the solution of given differential equation, which was d square y upon dx square plus xy equal to 0. So this is the solution of this differential equation. Thank you very much.